Okay, we're looking at oblique impacts again today. If you read the question, we're looking at a smooth sphere of mass m collides obliquely with a smooth sphere of mass 2m, which is at rest. Before impact, the line of motion of the lighter sphere makes an angle A with their line of centers. Now, this is very important. So what we have here is before impact, the line of motion of the lighter sphere makes an angle A with the line of centers. So what that means is that we have this situation here, that it's approaching the first ball at an angle A to the line of centers, and we do not know what the velocity is, so we call it u. Okay, the next part of this statement is that after collision, it makes an angle B with that same line of centers. So after the collision, again, we do not know what the velocity is, so we're going to call it V. And what you have in the diagram is there's the angle V, and it is making an angle B with the line of centers. Okay. So once we've established the information from the question on the diagram, we can go to the traditional approach of doing our before and after diagram. Now, what we now need is we now need to have an expression for the velocity in here. And in order to get that, we're going to be resolving u. We're going to be resolving u through the angle A. So at this point, you would be expecting u to be sort of knowing what the answer is, and the answer is going to be u, so it's going to be u cos A. To get the vertical component for the first sphere, you're going to be resolving about this pivot position away from the angle A, so we're going to be resolving this way, and it's going to be u sine of the angle A. So we put that on the diagram. We also know that the second object, according to the question, wasn't moving. So the horizontal velocity is 0 and the vertical velocity is also equal to 0. We're now going to label the after diagram. And the after diagram for problems like this is always labeled as V1, V2, and V3. Always. Now what we're going to do is, we already know from previous work on this course, is that we're going to be transferring information from the original diagram to the new diagram. So we know that V3 is equal to u sine A, and we also know that the speed here is equal to the 0. So we transfer that information across, and we've got u sine A and we've got 0. Now, at this stage, what we're going to do is we're going to go back to the original diagram, and we're going to look at this velocity here. We're going to look at the velocity v, and we're going to resolve that through the angle. And don't forget that v is the velocity after impact of the first sphere. So when we resolve v through the angle B, we get v cos beta, and that's going to go into this slot here. Now we're going to resolve away from the angle beta. When we resolve away from the angle B, we are going to get a vertical velocity, which we're going to write here. And that vertical velocity is going to be v sine B. And that now means that we've got two expressions for V3. We've got V3 from the transfer earlier on is u sine A, and we've also got V3 from the question is v sine B. So we can now write down here that u sine A is equal to v sine B, and we're going to be using this later on in the question. It's an extremely important piece of information. Highlight it for use later. Now we need to put our masses on the diagram, and the mass of the first sphere is m and the mass of the second sphere is 2m. We're going to use conservation of linear momentum, which says that momentum before is equal to momentum afterwards. The impact is along the line of centres, so we're only looking at conservation. There's only conservation linear momentum applied in the horizontal direction. So we've got mass times velocity, so we end up with m on u cos A plus 2m on 0 is equal to m on v1 plus 2m on v2. We're now going to cancel out the m's, and we're going to rewrite this as v1 plus 2v2. So we've got v1 plus 2v2 is equal to u cos A. And we're going to calculate what v1 is from the equation by solving conservation linear momentum with Newton's experimental law equation. So we need to now work the Newton's experimental law equation. So we've got v1 minus v2 is equal to minus e on u1 minus u2. Now v1 is quite simply v1, v2 is quite simply v2, e, we were told in the question, is 1/3. Our u1 is u cos A, and our u2 is equal to 0. So we've now got v1 minus v2 is equal to minus 1/3 u cos A. Now I'm going to eliminate the v2 from both equations, and the way I'm going to do that is I'm going to multiply the Newton experimental law equation by 2 and write it under the conservation of linear momentum. So I'm now going to have 2v1 minus 2v2 is equal to minus 2/3 u cos A. And when I add these together, I'm going to get 3v1 is equal to, well, 1 minus 2/3 is going to give me 1/3. So I've now got 1/3 u cos A. Now we're going to multiply across by 3 in order to get rid of the fraction. So we're now going to have 9v1 is equal to u cos A. Now it's very, very important to note that earlier on we had established that v1 was also equal to v cos B. So we'd already established earlier on that v1 is equal to v cos B. And we're now going to substitute for v1 in the equation that we have just derived. So we're now going to end up, well, since v1 is v cos B, we're now going to end up with 9 on v cos B is equal to u cos A. At this stage, we need to pause and look at what the question is actually asking us. And what the question is actually asking us is to prove trigonometric identity, and the identity that it's trying to get us to prove is something involving tan. So what we need to certainly have in our heads, in thinking, is what do we know about tan? And what we know about tan is we know that tan is equal to sine divided by cos. And we've got two equations involving sine and cos. So I'm going to bring the first one down, which is u sine A is equal to v sine B. I'm going to write it in this empty space. So we've got u sine A is equal to v sine B. And that's equation number one. And I've got a second equation here, and I'm going to write this underneath the first equation, except on the left I'm going to write u cos A, swapping it from the way it was written on the left hand side, is equal to 9v cos B. Now these two equations are equal to each other, so I'm going to divide the left hand side by the left hand side, and that will be equal to the right hand side divided by the right hand side. So I've now got u sine A divided by u cos A is going to be equal to v sine B over 9v cos B. Because of this neat trick, I can now cancel out the u's, and I can now cancel out the v's. And from what we said earlier on, we know that sine A divided by cos A is equal to tan A. And we know that on top we've got a 1, so we've got 1 over 9. And we know that sine B divided by cos B is tan B. To finish this problem off, all I've got to do now is multiply both sides by 9. So to finish it off, I've now got 9 tan A is equal to tan B, and I've shown what I need to do. So just so that you can see the whole page, just going to pan out, and what I'm going to do now is tell you what the work set is. Now, the work set is going to be exercise 7D, page 121. And in the first instance, I want you to do numbers 1, 2, and 3. And when you've successfully completed numbers 1, 2, and 3, and we've corrected them in class if needs be, I want you to move on to doing numbers 4, 5, 6, and 7.